Our second speaker is Viktor Chuchurski. And Viktor is an application security engineer involved in white box audits of code. And today he will deepen on database transaction and the potential risk they put in place. So Viktor, the stage is yours.
Hello. Hi, welcome again. Thank you for coming. So I just want to take some time and talk a little about databases, database transactions, and the concurrency that happens on the database level. So a little bit about me, even though I had a nice introduction. My name is Viktor. I work as an application security engineer for Doyensec. We're a small consultancy, mostly focusing on white box security audits. So my days are, I spend my days reading client's code, and I've done my fair share of software development in the past. And here are some socials if anybody wants to get in touch after the talk. So it's always best to start off with an example, and this is a small snippet of Go code implementing a transfer function. And I apologize if anybody in the audience is not familiar with Go, but everything is pretty straightforward, and we're not using anything language specific, so it should be fine. And we start right off by defining the transfer function. As you might expect, we just accept a source, a destination account, and the amount to be transferred between them. First thing we do is connect to our database, and we start off by initiating a database transaction. And in case anybody in the audience is not familiar, a database transaction is defined as a unit of work on the database level, which encapsulates 2 or more database operations, and the database engine actually ensures that they would be fully executed independent of any other executing transactions at the time. Now we just move on to the actual meat of the transfer function, the business logic, and we start off by first reading our source account from the database and doing our due diligence input validation, checking whether the amount that was requested is valid and if it's within the bounds of the balance that the source account currently has in the database. If the checks fail, then we just roll back the transaction, effectively telling the database server, ignore everything we did prior, and drop any changes. However, if the validation goes through, meaning that what we requested is correct, then we start off by actually performing the transaction. We first subtract the requested amount from the source account, add it to the destination account, and wrap up everything by simply committing the transaction, telling the database server, okay, we are done here, feel free to persist the changes to the disk. So let's see how all of this looks like in practice. And I hope the demo will work. So I just have the snippet of code that we saw running in the background. And we are going to simply start off by, actually, let's do it this way. It's going to be bad. I can't see. But OK, let's start off by first looking and see what's currently in the database. And if we just dump the entries, we see that we have 2 entries. Alice that has a balance of 100, and Bob that has a balance of 20. And now we can try to do the transfers between them. And actually, let me do it this way. 1 second. Oh, this is bad. I'm sorry, 1 second. Oh, OK. OK, perfect. So now we can start off by performing our transfer. As you can see, we're just transferring an amount of 50 from Alice to Bob. If we do this, we see everything worked correctly. If we check the state again, we see that the actual transfer happened. We perform the transfer again. It's going to go through. We try to do it a third time, and we see, OK, yeah, the second time it went through. And if we try to do it a third time, we'll see that we get an error, invalid balance, because we fully emptied out Alice's account. Basically, any further transactions will be forbidden. So now we can reset our state and try something different. Basically, what we're going to try is doing an abnormal requests to the application. So this was like something you would expect when you're developing an application. The user clicks on the UI. One transaction goes through, another one goes through, all is fine. Let's try something more intensive, let's say. And to do that, we're just going to utilize a simple Go client that basically does the same thing, But the only difference is it will try to perform multiple transfers in parallel. And this go keyword simply means just do the transaction in a separate thread. So basically what we're going to do is 10 concurrent transfers to the endpoint. And let's see what this does in practice. And if we simply run the client, we kind of expect to see the same thing as what we did manually, 2 successful transactions, and then the rest will fail. And if we run this, we actually see something different. If I just make it a bit bigger, as you can see, the status code that was returned for each of the transactions was 200, which doesn't really add up. And if we go back and actually check the state in the database, we see something really weird. We see that Alice has all of a sudden a negative balance. Basically, we managed to overdraw her account. So what's actually happening here? So let's go back to the slides, and let's try and examine the source code and see what's here. Let me just fast forward through this. So taking a step back and just looking at the source code, we see that more or less everything seems fine. We ensure that everything is going to be fully executed by using a transaction, so we're not doing partial updates. We do our input validation, we check the balance, but something is definitely wrong, as we saw in the demo. So if we don't see anything obvious on the application level, the next best thing, let's look at what's happening on the database. And the easiest way to do that is by simply enabling database logging and seeing what's actually being executed. And if you look at the logs, it basically looks something like this. This is basically what you're going to see if you were to enable logging and run the demo that we saw previously. And if we do some cleanup, like renaming the transactions and some color coding right off the bat, we see something really interesting. So recalling back to the definition of a database transaction, the definition states that it's a unit that is executed independently of any other transactions on the database. But the logs show us something different. As you can see, operations belonging to different transactions end up being interweaved and executed not as a single unit. And the reason that this happens is due to how databases implement the actual transaction execution. So like any other high-performance piece of software, databases aim to execute as much of their workload, incoming workload, as they can in parallel. And the way they do that is by implementing workers, basically small components that are designed to execute the transactions, and they work in tandem with a scheduler, which will basically inspect an incoming transaction and assign it to the appropriate worker based on some conditions that might be baked into the scheduler. So all incoming transactions will be designated to a worker, and the workers will go ahead and execute those transactions. So basically, with this, what we end up having is a model of an environment where we have concurrent execution. And most of you might be familiar, but with environments with concurrent execution, a common problem that we see is concurrent access or modification of shared resources. On the application level, that's known as a data race or a race condition. And databases are not immune to that. However, on the database side, those types of problems, given the definition, the ANSI standard for the SQL language, they are known as read phenomena. And the standard defines 3 read phenomena, more specifically dirty reads, non-repeatable reads, and phantom reads. Technically, there's a 4th one, but currently it doesn't apply to what we're going to talk about here. So to understand everything better, let's look at them in more detail and actually understand what kind of problems can arise on the database level. So starting off with the dirty reads, let's look at a scenario where we have 2 concurrently executing transactions. The first transaction will start off by reading some entry A from the database that currently at that time, let's say, has a value of 5, and it will update its value to 15. At that time, another transaction starts executing and performs the read on the same entry and gets a value of 15. Now, if this phenomena actually happens on the database level, and we assume that, say, a scenario happens where transaction 1, for some reason, decides to revert its changes, maybe due to business logic reasons or something crashed on the application level, the changes will not be committed. The changes that transaction 1 made will not be committed, meaning that the state of the database will persist by having the value of A be 5, but transaction 2 will continue executing under the assumption that the value of A is 15. That causes inconsistencies and may cause problems on the application level. Moving on, next we have non-repeatable reads, and this is a phenomenon that happens if a single transaction performs the read operation twice, the same read operation twice. And let's look at an example to actually understand what does that mean. Again, we have two concurrently executing transactions, and we start off by transaction 1 reading an entry A, which has a value of 5. Transaction 2 is going to do the same thing and get the same value. But at that time, a context switch happens, perhaps, and transaction 1 continues executing. It updates the value of A, committing, and ultimately changing the value of A to 15. Now, when transaction 2 continues executing and repeats, for some reason, executes the same read again, now it's going to get a different value. Now it's going to get the value of 15, basically breaking the assumption, changing the world state underneath the feet of transaction 2. And this, given a specific context on the application level, again, can cause problems, inconsistencies, and ultimately lead to some vulnerabilities. And phantom reads are just a generalization of non-repeatable reads. While non-repeatable reads were concerning themselves with repeatable reads on a single entry, phantom reads are repeatable reads on a set of entries, basically a read operation with some predicate attached to it. So again, we have the same scenario, two concurrently executing transactions. The second one will start off by reading all entries which are greater than 50. And at that time, let's say that those entries are A and B. In parallel, the first transaction will go and add a new entry to the table, which has a value of 80, and go ahead and commit that value. And when transaction 2 goes and performs the same read again, now it will get a different world state, again, leading to problems, as with the previous scenario. Now, the SQL standard tries to define these weird behaviors, concurrency issues that arise on the database level, but the real world is much more complex. So on top of what's already specified in the standard, in the real world, we can also observe stuff like reads queues, writes queues, and lost updates. We're not going to go into detail on all of them, but we're going to see a few examples that actually show what they actually mean. And if anybody's interested, this is a nice article, kind of like an addendum to the ANSI standard that goes ahead and specifies all of these read phenomena. So if anybody's interested, I highly encourage you to take a look at that paper. So we have concurrency problems. And like at the application level, we try to solve them by using locks. On the database level, we have two types of locks that are common. The first one is called the read lock. So as you might guess by now, the read lock is a lock that will be placed on an entry whenever it is read from the database. They're also known as shared locks, which basically means that multiple instances of this type of a lock can be placed on the same entry at a time, meaning that multiple read locks can be acquired on the same item in the table. On the flip side, we have write locks. These are placed whenever we update something in the database. And they're also known as exclusive locks, basically meaning that only one write lock can be active on a particular entry in the database. And the table on the right-hand side shows the relationship between them. So if we have no active locks, it's a free-for-all. Any type of lock can be acquired. If there's a shared lock active, another shared lock is allowed to be placed, but exclusive locks are forbidden. And if an exclusive lock is currently active, then no other locks are allowed to be placed on that particular table entry. And one interesting thing to note here is that under normal circumstances, by just using default behaviors of databases and database transactions, select statements will not acquire any locks. Just keep this in mind. We're going to come back to it in the next slide. So now we know the problems, we know the solutions that databases provide, but we still don't have a full picture of what actually happened in our demo, what allowed us to bypass the checks and basically overdraw the account and leave it in a negative state. So the best way to understand it is just drawing another parallel to what happens at the application level. So if we have concurrency in our applications, we use locks to basically segment out a set of operations and allow only a single transaction, only a single thread, for instance, to execute that set of operations. And that is also known as a critical section. And we can kind of apply the same way of thinking to database transactions. And if we look at the SQL that was executed by the demo that we saw before, our Go snippet, and think about where and when the locks are placed, we can see that the first operation being a select, as we mentioned in the previous slide, under normal circumstances will not place locks, which means the update will be the first operation in this transaction that will place a lock on the entry that's being updated. meaning that ultimately we end up with a critical section that's placed somewhere around here. And taking a step back, now it's kind of obvious what actually happened in the demo. We have a clear data race on the read operation, and which ultimately leads to an exploitable race condition, as we saw. So now let's actually look at the execution steps and how operations are executed on the database when an issue like this arises. And this is the same, initially, first we're going to look at the same exact pattern that we demoed at the beginning. So we have a scenario of 2 concurrently executing transactions, and we have an account with a source balance of 100, another account that's going to be our destination with a balance of 20, and we're going to transfer the full amount from the source to the balance. And we start off by executing transaction 1 and reading the value of the source account, which at this time has a balance of 100. And transaction 2 is going to do the same thing and get the same value. Continuing on, the first transaction, the value is now returned back to the application level, and both transactions will be basically performing the amount validation that's implemented at the application level, and everything seems valid at this point. We have 100, we're trying to transfer 100, all is good. Continuing on, the first transaction will will continue executing, and we'll try to update the balance of the source account by subtracting the transfer amount. At this point, a lock will be placed, and the balance of the source account will be set to 0. If transaction 2 tries to perform the same write, it will encounter the active lock, and at this point it will stall and wait until the lock is released so it can continue executing. Which means that if we assume that these are the only 2 transactions that are currently executing, the first one will be now free to finish up with, all of the leftover operations. And in this case, it's the last write which will update the balance of the destination account, adding the transfer amount, setting it to 120, committing, releasing the locks, effectively changing the state of the database where the source balance is set to 0 and the destination balance is set to 120. Now with the locks released, the second transaction can continue executing. It will try to, perform the write, place an exclusive lock, and subtract 100 from the current balance of the source account. And now notice something. Initially, when the transaction read the value of the source balance, it was 100, and it performed the amount validation based on the assumption that the source account has a balance of 100. But now, due to the concurrent execution of transactions, another transaction changed the worldview of the second transaction, which means now when the second transaction performs the write and subtracts 100 from the current balance of the source account, it will subtract 100 from 0, which means now the second transaction will set the balance of the source account to minus 100. The second update will perform the same thing and add 100 to the current destination balance, setting it to 220 and committing, and basically leaving our database state with an overdrawn source balance account, effectively the same exact scenario that we saw in the demo. So the key thing with this example is that the amount calculations that were performed by the transaction were performed on the current state of the table entries in the database. Some of you might be thinking, okay, now we can just move stuff around and basically perform the calculations on the application level and then pass everything down to the database so it gets persisted. So let's see how that looks like. And this is the same example, but just modified. And you can notice right before performing the update statements, we are performing the calculation on the application level and just passing the new balances down to the database. And let's see what's happening here. We have the same exact scenario as the previous example. And we start off, both transactions will perform reads and get the same values from the database. Both of them will perform amount validations and amount calculations based on the value that they just read from the database. And now we start executing our writes. The first transaction will perform a write and set the balance of the source account to 0. The second transaction, if it tries to do the same thing, it will encounter a lock and wait, allowing the first transaction to execute, which will perform its final write, set the balance of the destination account to 120, and commit, releasing the locks and changing the database state where the source account has a balance of 0 and the destination has a balance of 120. Now, the second transaction will try to do the same thing. It'll place a lock, and it will also set the balance of the source account to the value that was calculated in the application, on the application level, and set it to 0. Same thing with the destination account, ultimately committing, and basically not doing anything. leaving the database state in the same, in the correct expected values that we want to have if we perform such a transaction. So what we end up having is potentially a weird behavior where we were able to execute the transfer twice, but we didn't end up corrupting the database. And some of you might be thinking, yeah, well, this is probably fine. Well, that really depends on the overall context of where this is executing. If we assume that something like this is being executed in an application that's designed with say, a microservice type of architecture, where we have a main application that accepts incoming requests, and another downstream service that will actually perform the physical transaction. So basically, the main application is going to perform our validation and update our database state, while the service is going to perform the physical transfer between both accounts. A usual symptom of these types of architectures is that the downstream services fully trust whatever the main application sends down and don't perform any additional validations. They figure that whatever the main application sends down here has already been properly validated, so I don't have to think about it that much. I'm just going to do whatever I'm designed to do. Which means that if we have something like this, with the previous example where we were able to call the transfer function twice, we end up calling the downstream service twice, or n times depending on how reliably you were able to hit the race window, and again, leading to some form of exploitation where we will be able to overdraw our accounts or perform additional transfers that technically should not be allowed to. And this is not the only way to exploit this type of scenarios. We can also do something like transferring the balance of the source account to two different destination accounts. And in this case, just note that we have a total balance of 130 before doing any performing any transactions. So let's see what happens here. We start off basically the same thing. On the left-hand side, we will be transferring to destination A. On the right-hand side, we will be transferring to destination B. We go through the same song and dance as the previous example. We perform the validation, we perform the calculations on the application level, and then pass everything down to the database. The first transaction will set the source balance to 0. The second one has to wait at this point. The first one will continue executing. It will set the destination balance to 110 and commit, which leaves the second transaction free to complete its remaining operations. It will also set the source balance to 0. It will set the destination B's balance to 120 and end up committing. And now what we end up is basically printing money out of thin air. We started off with a total balance of 130 and ended up with a total balance of 230, basically duplicating whatever the source account had in its initial state. And this is all fine, and some of you might be thinking, yeah, but I don't really have a financial application, or I'm not testing that type of thing. And this can also be abused given the context of the application. It doesn't strictly apply to financial stuff. It doesn't strictly apply to monetary transfers. So let's assume that we have an application that has some sort of a loyalty point system where users earn some points while they're using the application. And because and the points allow those users to get some sort of discounts on subscriptions that you might be offering in the application. So if they have enough points, they get, say, a 50% discount. And now because the holidays are coming, you introduce a new holiday limited time offer where users, friends can pool their points together, basically allowing them to use the discount without having acquired the full required amount of points. And let's assume that we have a user Alice that doesn't have any friends but still kind of wants the discount. So what can Alice do is basically try and perform multiple operations on the application where she would basically try to add herself multiple times to the same pool. And let's see what happens in this case. So all of them are basically going to start off by reading the database state, which simply tells them that, yes, this specific user has acquired 100 points, and those points have not been pooled yet, which means that, yes, she is allowed to add her points to the pool. So this verification is going to happen on the application level and pass, and now we start off updating our database state. The first transaction will update, the second ones will have to wait, and the update will basically set Alice's points to 0, mark her account as if her points have already been pooled, and we start off by having our pool total points in the pool of 100. Next, let's assume that the second transaction is going to perform the same update. it will update Alice's account to mark her points as pooled and add 100 to the total pool points, now changing the points in the pool to 200. And you can kind of assume what happens with the same transaction, and we ultimately end up basically abusing a limit that the application imposed and allowing Alice to pool her points n number of times, allowing her to basically get the discount ultimately for free. So now, this is nice, and let's talk a little bit about exploitation in the real world. If you're testing an application, usually for race conditions, it's fairly straightforward how you would to exploit, and barring some weird interactions that you would do to actually reach the functionality which is vulnerable, exploitation usually can be done with some multi-threaded for loops. We're back, perfect. So as I was saying, exploitation usually is fairly straightforward. Just run a thread with multiple loops, making the concurrent requests, and you're going to be good. If you're a pen tester, you most likely have Burp Suite. You can do the same thing with Intruder. And because real-world exploitation of race conditions is a bit more difficult, Burp Suite has a nice tool called Turbo Intruder, which includes actual implementation of research that James Kettle did on exploiting race conditions, and it basically allows, it provides you an easy way to exploit the last byte sync or the single packet attack, effectively allowing you to exploit the TCP stack, abuse the TCP stack actually, and deliver a bunch of requests to the target system at the same time, making exploitation of race conditions a bit more feasible in the real world. Now that we've broken everything, let's try to fix it. So multiple ways we can go about fixing these types of problems. The first one we're going to look at is optimistic locking. And optimistic locking is a method where we assume, is a technique where we assume that nothing is going to go wrong, and we just do some validations at the end of the transaction, basically checking whether the values that we are operating on have changed under our feet while we were executing. And the common way to implement this is by introducing a logical clock. Usually it's a version column on the table that has the sensitive information, and what we ultimately end up doing is adding an additional check at the end of the transaction, verifying that the version that we saw initially when we read the value is the same version that we have at the end of the transaction. And in code, it looks pretty straightforward. The version column is just a simple int, or however you want to implement it, and the updates just need to be, the update statements just need to be updated by adding the version verification and checking whether the version changed while the transaction was executing. On the flip side, we have pessimistic locking. Now, if optimistic locking assumed nothing is going to go wrong, pessimistic locking assumed that everything is going to go wrong, which basically means that we acquire any required locks at the start of the transaction and then don't release them until we are sure that we have made the necessary changes and we are ready to commit our changes to the database. We can implement pessimistic locking in multiple ways. We can do it on application level, basically using semaphores or any locks that your tools of choice might be are providing. However, I personally would not recommend this because concurrent programming is pretty difficult, and any mistakes by implementing this manually will basically lead you back to square one, where you have a vulnerable application. Another way to implement pessimistic locking is on the database level. So when you do the transactions, when you do queries, you can specify, you can basically tell manually the database server, please place a lock on this particular entry. I'm probably going to update it in the near future. And the way to do that is by using the for share and for update modifiers in a way where you basically add it to the end of your select query, telling the database server to place a lock. The difference between them is that the for share will place a shared lock and the for update will place an exclusive or a write lock. It's worth noting here that this is not an ideal solution because weird scenarios can arise, such as this one here, where the first transaction, while it did perform a read with the for update and the lock was placed, the second transaction was still allowed to read that value and operate under the assumption that it will not change. And the first transaction committed some changes, but the second transaction didn't see those changes, ultimately performing another update, overriding whatever the first transaction did, and this is a version of the lost updates that I mentioned initially. It's also worth noting here that higher isolation levels may prevent this behavior, And that leads me nicely into transaction isolation levels. And this is kind of like the recommended way of how you would go about performing concurrency control on the database level. Transaction isolations are basically properties of database transactions that are developer controlled, user controlled, that you can specify at transaction creation time, which signals to the tells the database server to which level you want your transaction to be isolated from other concurrently executing transactions at the time. The SQL standard defines four levels of isolation. The gold standard is serializable, which essentially removes all parallel execution and makes it so all transactions are executed in a serial manner, effectively removing any possibilities for the race conditions, the issues that we saw initially. However, this is not something that you really want for your entire application. Imagine removing all concurrency from your database. Your application is going to crawl down, basically going to not stop working but become extremely slow. So because of that, the other isolation levels will basically lower the guarantees or remove some of the guarantees that the serializable isolation level provides. The other isolation levels are known as repeatable reads, read committed, and read uncommitted. So as we go down the list, you will be able to see more and more of the read phenomena that we saw initially. And this is also shown on the table. So for instance, if you're using read committed, you won't see dirty reads, but you're probably going to run into non-repeatable reads and phantom reads. Now, when I mentioned initially that select statements do not place any locks under normal behavior with default configuration, that basically means that the transaction will, without specifying a transaction level, will run with the transaction level that's defined as the default for that particular database vendor. And as it turns out, the most common default is read committed, which means that if you're running a database transaction on some critical operations and you don't specifically set the isolation level, you will be running with read committed, and there's a highly likelihood that your application is vulnerable to these types of issues. And a lot of this is really subject to how the database vendors decided to implement stuff. For instance, MySQL's default is set to repeatable reads, so you're a bit safer using MySQL, but again, it's not ideal for business critical stuff. Also, the actual behavior of the isolation levels is different. For instance, Postgres' repeatable reads is a bit stronger than the repeatable reads that are defined in the standard. And basically, Postgres defines something that's called serializable snapshot isolation, which sits somewhere between repeatable reads and serializable. And one standout database vendor here is Oracle, which only supports serializable and read committed as its available default, as available transaction isolation levels. But the serializable that Oracle provides is actually equivalent to snapshot isolation, which means it's not serializable. Ultimately, it might allow for some exploitation. So if you have Oracle and you set serializable, I advise you to look at the documentation because it's not actually ideal and it's not the serializable that's defined, specified in the standard and what you might expect if you're using the serializable isolation level. And finally, a little bit about detection. It's setting the isolation level is just a pattern in your code that you can just grab out, search for it, and write some detection rules. So, for instance, this is a simple samgrep rule that it will try to detect raw SQL transactions defined in the code that don't specifically set or define the isolation levels. If you're using an ORM, setting the isolation level is going to probably be calling some parameter, calling a function that sets the isolation level before the transaction is actually created. This is an example of a samgrep rule that's going to search for transaction creation without specifying the optional parameters where you would define the isolation level. And finally, this is another example where it will detect the optional parameters, but it will try to find the scenarios where the isolation level is still omitted from the optional parameters. This is unfortunately too noisy for a lot of applications, but it's, in my opinion, a good starting off point where you can kind of get an inventory of all the transactions that you have and then look through them and see whether there are places in the applications that can be tightened up. Now, a lot of this stuff is not new. The SQL standard came out in, I think, 98, and the addendum, which added the isolation levels, came out at around 92. So this has been known for a long time. But the unfortunate reality is that this is not this is a thing that it's still not common between developers. It's still something that's lacking in terms of people being familiar with it. So we see these types of problems in the audits we do, and we also see them in the real world. These are just two examples of cryptocurrency exchanges that got exploited through this method. So if you click on the links, you're going to see a description that really description of an attacker was able to perform a large number of requests to the system in a small amount of time, basically describing exploitation of a race condition. And finally, a few takeaways. Databases, while they are an essential tool for today's applications, do introduce a layer of complexity that's initially hidden from the developers. They introduce another level of layer of concurrency that we need to be mindful of. So always think about additional dependencies that you add to your application. And while we usually treat them as a black box, they shouldn't be a black box. They have great documentation. Postgres is a standout here. MySQL's documentation is also pretty well written. So I would advise look through the documentation of your preferred tool of choice and see how they actually implement the isolation levels, or potentially if they provide additional functionality that other database vendors do not have, which might be perfect for your use case. And finally, again, it's not a black box, so you can play with it a little bit. You can simply spin up Docker containers, spin up 2 parallel terminal windows, make 2 connections, and start executing transactions. You can inspect the logs. You can see where the transactions stall. You can see where how the database state changes, and basically get familiarize yourself with how the tool actually operates. Finally, you can find all of this in a different form on the link below. And the Git repo has some setup where you can quickly spin up Docker containers, and it has 2 sample apps, one written in Go and one written in Node, so you can easily play around with this stuff yourself without going through the setup, all of the setup steps. And with that, I'm going to wrap up. Thank you, everyone, and I'm not sure if we're going to have time for questions.